they declared that the recent summer was the third hottest summer on record in the United States. It's just so silly.
Yeah.
I didn't even turn on my air conditioner.
Well, I had the temerity to mention to some people yesterday that my scientific group had been talking about this, and something was drawn to my attention that I hadn't noticed. It was one of the things I think you put up in 1971, if I'm not mistaken. There was a big conference in Brown University in Rhode Island, one of the Ivy League universities, and they wrote to presumably President Nixon, because it said, "Dear Mr. President, we've just had a major conference of all the experts in climatology from the United States and all over the world, and the consensus is that we're in a very difficult situation. Hence, we're writing to you now. We believe that because of the extreme pollution on the Earth, the sun's energy is not getting through. And within another 5 years, we're going to have another ice age. It'll be like we had 12,000 years ago." So I said, it appears that luckily Nixon didn't do anything about it. Thank you very much, Denny. And as you have announced, the calling notice had special relativity and the many speeds of light. However, the title I adopted when I was making up these slides a few days ago was Hertzian electrodynamics and non-constancy. But I think we'll be covering the same thing. And unfortunately, in this subject, though I hope I'll be making some reasonably cogent cases for my thesis, that C is not a universal constant in this sense, and indicating that I hope it ties in with experimental results. It's an area in which I think the words of Henry VI in Shakespeare's play does not apply. Thrice is the arm that has his quarrel just. Thrice is the arm that has a quarrel just. So if you make just arguments, you're quite strong. Well, that isn't the case, because we have come across cases where ad hoc hypotheses were introduced to save existing preconceptions, and we talked last week, of course, about goalpost changing. So, however, I'm strengthened, I'm armed in Henry VI words, in the sense that I don't think I'll have an altogether unsympathetic audience today. So my general thesis is that the Hertzian substitution of total for partial time derivatives have usually been used in the Maxwell equations, and indeed by Clerk Maxwell himself. But if you substitute the total derivative for the partial derivatives, you get a more rational dynamics, which actually is used in all other areas of physics. So it's strange that electrodynamics would be exceptional, as in other areas of general dynamics, this does not involve any such notion as a constant radiation transmission speed independent of observer motion. So if the observer is moving towards it, doesn't make any difference. If he's moving away, it doesn't make any difference at a very high speed. So just it's a continuation of some of my earlier work where we had keywords like wave propagation, Doppler effect, special relativity, and electromagnetics, which I'll be returning to there. So this is just maybe a slide to not to go through in too much detail, but just some of the earlier work which I've been involved in, on which this is developed. Things like I've updated, so I say, the electrodynamics of moving bodies. I published that in a Galilean electrodynamics, and I presented at a conference in Russia in 2004. The proceedings were published in 2005. I made some comments on the Michelson-Morley experiment in 2010. I wrote another paper on electromagnetic waves, which I gave a presentation actually to the NPA on shortly afterwards in 2018. And more recently, and again, another short presentation, 2021, when it was a little complicated, as Danny, I think, mentioned in the introduction, that a couple of the equations had been omitted. But anyway, I gave a presentation which I hope was not too unclear. So we can get back to those if anybody's interested. Now, just one slide on introduction, because I know we are a bit short of time. The total derivatives. You know, I think actually my cursor here, you know, this thing is like a total derivative, or sometimes a convective derivative, or a material derivative, you might see in some of the texts. So delta by delta t is the partial time derivatives plus the dot product of any velocity. What I've done, I've gone too far. Of any velocity, it must be this tertiary thing, and the nabla operator, or del operator. So I don't know why it's going forward. I better keep my hands away. Yeah. So the total derivatives are used in fluid dynamics. This is quite general. We do that. The capital D by dt terminology was introduced by Stokes actually. There is a good precedent for using all these terms in classical dynamics. So it's used. Why not use it in electric dynamics? I don't know why it hasn't been used. Well, we'll maybe theorize or postulate some possible reasons later. But anyway, I'll be hoping to show you, without going through all the mathematics, but giving the basic equations, that if we do that, it would lead to a wave equation of that form. You see, if V is 0, you just get the standard wave equation. U is any disturbance. It could be a pressure, or it could be you know, a force field, which is dependent on the spatial coordinates x, y, z, and the time coordinate t. But you have this extra term in there, squared up. Now, I claim that this obviates the necessity altogether of using Lorentz rather than Galilean transformations to preserve invariance. So sometimes, I think I may have said this at a previous occasion, Lorentz, if you leave out that term, well, then in order to preserve invariance, you have to change the Galilean transformations. So the Lorentz transformation is like a quick fix to try to change something which you have erroneously introduced, and you shouldn't have done that. It's almost like a golfer. You know, they say if you have a perfect golf swing, like Ben Hogan or something, you don't need to make any adjustments. But if you start with a poor swing, well, then the human mind knows you have to hit the golf ball. So you make all sort of weird adjustments, which mess up everything. So it's rather like that. And
Ian,
yes?
are you talking specifically about special relativity's Lorentz transformation, or are you including Lorentz's original transformation for the ether?
Yeah, indeed, because I think we might even have mentioned that briefly the other week. Today, I am addressing basically Lorentz transformations insofar as they apply to special relativity. However, I think I would have to say that my statement that I've just made applies in all cases, even to Lorentz transformations about a fixed ether, because he introduced what I consider a better model, where you do have a preferred frame, a static frame, and then you introduce these transformations about that. That's more rational than having all frames all over the place, whatever the relative velocity is the same. However, I claim that the same mistake was made by not allowing for this convective derivative term, and therefore the Lorentz transformations or Voigt transformations are really unnecessary. We can maybe talk about that later, Nick. It's a good point.
Yeah, thank you.
Right. So the third point is I wanted to say that, and this is specifically the Einsteinian composition of speeds. So if you have speed V1 and V2, the mathematics comes out that you just get two-speed addition, simple two-speed addition, V1 plus V2. Whereas in the Einsteinian case, you have V1 plus V2 over 1 plus V1 V2 over C squared, and that preserves the constancy of C. So if you have if V1 is C, for example, and V2 is 0.9 C, for the sake of argument, you'll get 1.9 C as the relative speed. Whereas if you put in the Einsteinian formula, you can never exceed C. For example, if V1 and V2 are C, you get 2C over 1 plus C squared per 2. So just is equal C. So okay. Now, so just maybe to illustrate this, the Clark-Maxwell equations there in the form which were introduced by the form was introduced by Heaviside, using the Gibbs type notations rather than the quaternion notations which Maxwell used in his book Electricity and Magnetism, which are the same, but they're just very, very prolix. So just to summarize them there, and then Heinrich Hertz came, and as we know, he introduced some sort of simple circuit like this, a resonant circuit with a battery and a coil and a capacitor, condenser as he would have called it in those days, and a spark gap. And then he was able to use that as a transmitter, an elementary receiver with a spark gap, which he was able to induce in the other side. And that's well known. And in fact, Marconi's early experiments, when he was a young boy really, in his villa in Bologna, did the same thing. He rang a bell from one floor of his house to another thing using the Hertzian waves. So this is well known, but actually Hertz was also a theoretician like Maxwell. Even though he had a very short life, he died in his 30s, middle to late 30s. But so what he did is he conceived of this delta by delta t being replaced by delta by delta t plus v dot nabla. So we're back again to that thing. So so you can see these terms in the Maxwell equations would be expanded out. Now I'll give you one term. V in the simpler case would be constant, and we'll deal with that. In fact we'll deal with a planar wave just to illustrate the principle. But we'll just write down the general equations where V is a variable. It's dependent upon the XYZ coordinates, and if you do that, you get this lot of equations here. So if you actually do that, you'll get there Faraday's law, Ampere's law, Gauss magnetic flux law, Gauss's electric flux law, and charge conservation law, and the Ohm's type law, and the relationship of displacement to electric field intensity, and magnetic induction to a magnetic field intensity. Whenever I get this cursor up, it seems to move on the slide if I just tip it. But anyway, these div V terms would go out in the case that V is constant. So we just have the, by the way, I just put one reference in here, could have been many, but this gentleman, Eisenman, MN, he wrote, I think Harry had been involved actually with him. He asked me for this paper, but he was giving him some advice as well. So we're going around in circles. But anyway, this chap, which I think maybe Harry and I had one email correspondence at least with him, back to Galilean transformation and Newtonian physics, refuting the theory of relativity, published in the Journal of Physical Mathematics in 2016. So he gives a neat derivation of all this. And if you look at the right-hand side here, well, as I say, let's take a planar wave in the x direction with y and z components vanishing, and the x component is u. So the Vx is u. Well, then if you work out the usual double curl equations and all this sort of thing, where you derive in modern terminology the wave equation, well, you get this, which is slightly more complicated. You get this, and you can see already if you divide across by 1 over c, if you multiply by 1 over course by c squared, divide by c squared, you get 1 minus u squared over c squared, which is, the square of the inverse of the Lorentz, the gamma factor. And However, even though that will come in, and you can maybe see at the moment why Lorentz might be considered a bit of a quick fix, it's neglected this middle term, this cross term, which my cursor isn't showing up at the moment. This one here. So so actually, but with a bit of manipulation, then you can get this equation, the next equation further down, which is this one here. So again, if u is equal to 0, you just get the ordinary wave equation, because it's just the difference of two squares, a minus b into a plus b, a squared minus b squared. You get that. But you can see sort of heuristically, or you can derive it, that the equation, in other words, if u is 0, you just get a general constants time. The solution is constant times the function of x minus ct and x plus ct. That's the Euclid equation. But here, the solution to the equation just above is x minus c plus ut and x plus c minus ut. And this k here, this constant here, if you multiply that in, you get kx minus k into c plus or minus ut. Well, k into c plus or minus u is omega. It's the angular frequency. So that really denotes the operation of the Doppler effect. So it's actually all coming together. You know, the c plus u, c minus u times k. Okay, let me see. Okay, so I come to Doppler then. I might as well come to Doppler. So classically, in the Doppler transitions operating in a medium. Now, again, I'm going back to fluid dynamics, and I'm going back to the classical texts and the Navier-Stokes equations and the Eulerian or the Lagrangian methods of looking at fluid dynamics. You know, the Euler system is where you look at one position in the medium and you see what's happening, how the density and the pressure and all the parameters are varying. And then the Lagrangian systems, you look at one particle and you look at how it's moving through the medium. So but you see, I say, well, let's not be hung up about the ether, and so the fluid of the electromagnetic, put it in inverted commas if you wish, I have no problem. The fluid of electromagnetic transmission is an ether, and it's all analogous. So, and very importantly, there is not symmetry. There is non-symmetry between source and observer motion. So in the classical situation, for purely source motion, so you have a source and you have an observer, and the observer is constant relative to the ether, which is your frame of reference, and the source is moving in it. Well, for that case, both observed frequency, the frequency always varies, by the way, when you have relative motion. So the observed frequency and f and the wavelength lambda vary, while wave speed remains constant. So the speed is independent, as observed, is independent of the speed of the source. You don't get a sort of a Ritz ballistic system. It's the same. And that is actually the way Einstein's postulate number 2 of the 1905 paper is written in the paper, on the first page of the paper, that the speed of the radiation is independent of the speed of the source. Well, I say, so what? I don't disagree with it, but so what? It's exactly the same for water waves, for air waves, for seismic waves. However, on the other hand, for purely observer motion, so the source is here in the ether. The ether could be moving, but we're using the ether as a frame of reference in itself, so it's stationary from our point of view. It's our frame of reference. The observer is moving towards it or away from it. And in that case, as I say, the frequency always varies. The observed frequency and wave speed c vary, while wavelength lambda remains constant. Now, there's the rub. I say no. For observer motion, of course, the c varies, and hence the talk, you know, as discussed with Denny, the special relativity and the many speeds of light. Here, there are an infinite number of speeds of light depending on how the observer is moving with respect to the source. Okay, so I'll give you just a few equations on that now in the next slide. So everything is as clear as mud so far. Nobody's interrupting me so far. Nick made a good point, which I think we will return to in a moment, actually, as we're finishing off. So, okay, let's go to the equations. So, O is the observer, S is the source. V is positive for relative approach. So in other words, if you have a source here and the observer is approaching it, V is we're just taking that convention. You can take the opposite convention. V is positive. And then if the observer is here and the source is moving towards the observer, V is positive. So the classical expression is actually the observed frequency is either 1 over C minus Vs or C plus V VO multiplied by the frequency of the source. If you combine them, you get that. So the first equation is just a combination of the two equations. But we can keep them separate because we're going to look sequentially at source motion vis-a-vis observer motion, which special relativity says is immaterial because that's the equation. The equation given in the 1905 paper reduces that. Well, it's in all the textbooks. Just look at your physics textbooks and it gives that. You're probably all familiar with it. That's the relativistic equation. V is simply the relative speed, VO minus VS. And it's symmetrical. Doesn't matter. You don't have a separate VO and VS. It's merely the difference between them. And we're using the same convention of plus is relative approach. Now, so just try to illustrate it there. Redshift, blue shift. Well, let's just perform an experiment. Now, I do confess I'm going to perform a thought experiment, but I don't know the answer. I want the answer by performing a real experiment, and we're going to propose that. Now, if you take VO equals VS equals V, so let's just take that, and let's perform two experiments. Let's keep the source stationary and let's move the observer towards it at V, and then do a second experiment, and we'll keep the observer constant, move the source towards it, and we'll use the ether as a frame of reference, and we'll measure any change of frequency. Remember that the frequency changes in either case. Now, according to the Einstein equation, there's zero difference between the two experiments because they're exactly symmetrical. Just plug it into that formula, and it's all the same in either case. So delta FO, the change between the two experiments in the observer's frequency measurement as a function of the source frequency is zero. However, if you expand out the two separate formulae for the classical case, you get, well, in the first case it's 1 over C plus Vs. In the other case it's C plus Vs multiplied by it. So if we use the convention that V over C is beta, well then it's 1 over 1 plus 1 minus beta minus 1 plus beta. You see, it's a different thing. In one case it's 1 plus beta, which is the numerator, and in the other case it's 1 over 1 minus beta, which is the denominator. They're not exactly equal. If you get the difference between those expanded out by the binomial theorem, you get that. And so if you neglect third order and higher, you get it's approximately beta squared. So it's either naught or beta squared. So for example, radar equipment transmitting at say 10 megahertz, and which can discriminate to 10 hertz, just say, in order to pick up this difference, which is quite small, the ratio being thus 10 to the minus 6, the speed of the relatively approaching object would have to be at least 1,000th of that. You know, in other words, the square root of it, of the light. So in other words, you know, 10 to the minus 3 times C. So the experiment, while quite feasible in principle, would no doubt be costly, requiring things like orbital satellites and much higher precision equipment. So it would be quite a costly experiment to do, but it would indicate this, well, it should indicate which one is right for all times. But I really, being a realist, I think I would have as much hope of persuading the authorities in North America or in Europe or in Russia or anywhere else or in China to perform this experiment as the late Dr. Carl Zapfi did when he approached NASA with regard to performing a Michelson-Morley type experiment in one of their space expeditions. I think he got short shrift. He was led up the garden path initially, but they just stopped engaging with him. It's just a source versus observer non-symmetry examples. So I just wanted to say a few more things about this. So what I have here is the Romer experiments, the Danish astronomer Romer, and I have the Sagnac experiment here. So I say that the Romer and Sagnac experiments are analogous regarding the composition of speeds. So the difference in time is the difference in 1/1 C minus omega r and the C plus omega r. So omega is the, well, in the Romer experiment, what we're normally told is the difference between the light speed traversing this extra distance when the Earth is successively in close to Venus with its Io satellite going around here, and when it's further away. That was performed in 1673, but in 1676 he performed further experiments when the Earth was in successive positive and negative quadrature. So in other words, when it was at right angles to the Jupiter, did I say Venus? The Jupiter satellite of Io going around here. So what happens is you have to take into account the speed of well, in this case, it's the speed of recession of the Earth from Jupiter, and the speed of approach of Earth from Jupiter. Omega is the the angular speed, and r is the radius. So that's v. So this is basically v approach, and that's v recession. So you see it's a composition C minus v, C plus v. And if you do that and you plug them in, well, he found that he got the speed of light. It worked out perfectly. There was no discrepancy. And fun enough, those experiments of Romer have not been published as far as I can see. I cannot see them in the textbooks. There were people like that American man who physicist who again?
Bradley?
No, Bradley's the English one. Much later, quite recently in the 1990s, Denny, who participated in one of those conferences in St. Petersburg before I did. Wallace, I think is his name. You're right to mention Bradley, because Bradley, of course, got the aberration, and I'm coming to that in a second. In fact, it's my last line, the Bradley aberration. So you've anticipated me well there. But anyway, so that's the Romer thing. Whereas, so that shows it's not symmetrical. Well, the equal aberration of binary stars. So in other words, when we observe the motion of binary stars, we get an equal aberration. The Bradley aberration, where he's the story anyway, he's on a little launch on the Thames River, and he noticed the pennant changing, not only when the direction of the boat changes, but also when the direction of the wind, but also when the speed of the boat changes. So, I mean, if you've been driving into rain, for example, which is not horizontally at your windscreen when you're driving on a motorway or something, if it's coming in at an angle, the faster you go, the more it appears to be driving right into your windscreen at right angles to the vertical. So the Bradley worked this out, and of course he got a very accurate view. Once you work out the speed of omega r, the speed of rotation of the Earth based on the astronomical observations and so on, and you plug it in, you certainly get V over C. Well, it depends on the formula. There's a general formula, but it's roughly equal to the sine or the tangent of the angle at which the star's position seems to be coming down. So you have to tilt your telescope forward in the direction of the Earth's motion to be able to capture the star, and you get this aberration, which varies throughout the year. But I also, and I think maybe this is one thing I haven't seen so much of. Maybe I'm a bit original here, although many of the ideas, I'm standing on the shoulders of giants, as Newton says. The Sagnac formula is analogous, because Sagnac in 1913, had the spinning table, and we're talking about speeds of 10 meters per second. These are not relativistic velocities or anything. And he observed a difference in the time and therefore difference in phase, where he had a source which was it was being deflected against mirrors, but this table is moving around this way, and depending upon whether the light is moving in the direction of the table or conversely, it arrives back at a different time at the receiver. So in other words, if you have an observer on the table, he would measure different speeds of light. He must, because it's the same distance. He's moving in tandem with the light. On the other hand, if you have an observer in the laboratory, well, then he postulates that there's a different distance. The speed is the same because he's not moving relative to that, but there's a different distance. Like when the light is going in the direction of the table, it has a shorter distance to go than when it's going the opposite direction. But by the way, that's a sort of a simplistic explanation which the special relativists give to indicate why this simple experiment, which on the face of it appears to conflict with special relativity, it doesn't really. They say, oh, the distance changes, but that's only from the point of view of an observer in the laboratory. So the non-symmetry is especially pronounced when we consider the equal aberration of binary stars, and also with the Sagnac effect. Well, let's just a few words of history here, because this actual type of difference in phase was first noted by a German postgraduate student by the name of Hertz in 1911. He was actually killed in the First World War, but as a soldier. But his equipment, his source and his photographic plate were fixed in a laboratory, and he only deflected it onto the table. Whereas in Sagnac's case in 1913, everything was on the table. So that shows that it's independent of the source velocity. It's actually working in the ether, which is being carried by the Earth. It's actually the Earth framed in ether, what I would call that. And there's a gentleman by the name of I had it written here, Polanyi, who sort of replicated Harris's experiments in a bit more detail. He knew all about Sagnac's experiments in 1913, of course. He did that between 1926 and 1928, and he had the emitter and the photographic plate in the laboratory, and he got very accurate, much larger variations because he worked with greater speeds and so on. So that showed that the light was moving in the laboratory frame. Now, there are some other experiments which I think are important. They started in 1939, but they were published in 1942 by two Frenchmen by the name of Dufour and Prunier. Now, what they did is they, like Sagnac, they put the equipment on the table, but then they had some other ancillary experiments which deflected the light onto mirrors which were in the laboratory all over the place, on the ceiling and so on, and then back to the table. So intermediate between source and observation, they deflected it into the laboratory. And I mean, you might imagine if these were separate equal frames that you'd just get ridiculous answers all over the place, but actually it made no significant difference. Now, those experiments seem to be almost secret. We don't see them in any textbooks or anything like that. And they were performed in Paris when Paris was under German occupation during the Second World War. So the published information didn't get out. Okay, that might be one reason. But why after the war with these experiments? But they basically showed again that the Sagnac experiment, which, you know, by all intents and purposes, shows that the special theory of relativity cannot be correct, that there are many speeds for the speed of light. However, that it is independent of the speed of the source, because once the source has emitted the light, it's carried in an ether. And we're talking about, you know, the Earth's centered inertial frame, which is basically carrying this ether. But anyway, I was postulating a bit on why these experiments hadn't come out. But you know, the Sagnac experiment itself, never mind the Dufour and Prunier and the Michelson Gale and the subsidiary experiments, they're not mentioned by Einstein or anybody else in the standard texts. So anyway, to me, this just evidently shows that there isn't symmetry between the source and the observer. Oh, let's see. So basically, I'm concluding that the electromagnetic radiation behaves as other waves transmitting in a medium and can be satisfactorily analyzed through partial differential equations using total time derivatives, including the convective term v dot nabla. And so this is, we will discuss this in more detail, and it will be worthwhile. But the Lorentz or Voigt transformation is thus, I say, rendered Ossius. Now, Voigt, of course, the German physicist in 1887, in his analysis of all things of the Doppler effect, came across transformations which were basically similar to Lorentz's. And again, I would argue, owing to the same simplistic analysis, but his analysis of the of the Doppler effect is not simplistic. I'm not saying that. I'm just saying that you know, not looking at a total convective term for velocity effects. So really, a bit later than 1887, in the 1890s, you had people like Lorentz and Larmor working very similarly, you know, developing from the Fitzgerald hypothesis and the Lorentz hypothesis and getting out these transforms. And then Poincaré coming around at the beginning of the 20th century and actually deciding to name them Lorentz transformation. So, so that's where we get the term Lorentz transformation. But I say it's actually rendered Ossius because it might be convenient in doing some, you know, everyday calculations, you know, maybe even for GPS and clocks and so on. But actually, if you're looking at a full mathematical analysis, you just go back to the original full basic fluid dynamic equations, and if you use those, you have no problem. You get an extended wave equation. And this is the bit I was trying to explain earlier, that I actually, yes, have, yeah. I was just looking at the more the Sagnac things there written down, but I have explained those already. So Newton's first law is interesting, you know, that a body will retain its state of motion or absolute rest. Well, unless it doesn't. Now, when doesn't it do that? Well, if it is moving, or if it is not moving, depending on your frame of reference, and if it encounters friction, well, then it will not go on forever. Or if it encounters air resistance. So Newton's first law is like an idealized situation for motion, unaccelerated motion, where there's no velocity change and where there's no velocity difference change. So you know, and yet we accept it. We say yes, we can work out the formulation of classical mechanics using Newton's first law. But we basically, in a way, it is only saying an object will retain its state of motion, except insofar as it doesn't. And I'll tell you when it does, and I'll tell you when it doesn't. So it does in an idealized situation. Now, Einstein, the first postulate in Einstein's theory is basically just applying the classical principle of dynamics to electromagnetic radiation and optics. Which is not really valid, because if there's a medium, well, then you automatically have a frame of reference with which to which we can use to indicate any motion. So in other words, the classical belief that you cannot measure or understand motion from within a frame itself, unaccelerated motion from within a frame itself, is vitiated because you have an ether about which to do that. And we talk about the ring laser gyroscopes, which allow, say, modern jet airliners to understand if there's any yaw, or there's any pitch, or there's any roll in the aircraft, just by looking at 3 different axes of variation. Because what they're basically doing is they're using the Sagnac effect to measure any phase difference between the light rays going in opposite directions in the circuits in these 3 mutually orthogonal directions. But that's because you have an ether as a frame of reference. So you might say, well, look, if there were not an ether, well, then you could not measure motion. People would say, oh, we're only talking about unaccelerated motion, but what's it called? These circuits that this Chinese gentleman Wang has done, Rubyong Wang has done an experiment where he has these optical fiber conveyors, and they're conveyed over long distances in a straight line, and the only part they have is it's like around the wheels of a tank, a military tank. You have this like a chain system going around, so that he's only using that system, this conveyor, to bring the light back to its original source, but he got exactly the same effect. So the argument, oh, Einstein doesn't apply to circular motion or motion in a circle, so you better forget about it. Well, the first postulates would only be true if there were no ether. So but as there is an ether, we can detect motion, and therefore the extension of the classical principle of relativity, the Galilean principle, to optics and electromagnetic radiation is not correct, really. Now the postulate 2, as I intimated earlier, which basically in its first state, the first time it is stated, merely says that the speed of light as observed is independent of the speed of the source relative to the observer, and I say is unexceptional and unexceptional. So it's something that one cannot take exception to, but it's really of no consequence. It's not exceptional. But becomes absurd when reciprocity to observer motion is invoked. So in other words, when you take the complete special relativity reciprocity of observer and source motion and apply that and say, well, it's independent of the observer motion, you get complete absurdity, which simple algebra, actually simple, very elementary algebra on composition of speeds, which maybe a 10-year-old could or 12-year-old could understand, would seem to vitiate that. In other words, it would fly against complete common sense, and the only way out of that is for the defenders to say, well, we have to put common sense and ordinary logic indeed out the window. And that's the only way you can accept it. And that was Einstein's genius. So, and as I said at the very beginning, unfortunately, we would hope that thrice is he armed that hath his quarrel just, in Henry VI's words. But in this case, there's a bit of an exception, because people believe in this theory for various political or historical reasons, and they're not willing to accept logical or experimental proofs, even if the experiment that I indicated earlier that might be undertaken to resolve the question of Doppler effect. And if it were found, as I believe, that the classical expression was correct and the Einsteinian one is incorrect, I'm sure there would be some other ad hoc hypothesis brought in to show why, in this case, special relativity doesn't conduce to the Doppler effect prediction. So, gentlemen, I think the only gentleman here today, thank you very much for your attention. I'll leave it there within the time for the second observation, and I'm sure we'll be able to have a brief discussion about the matters. Thank you.
Ian, this is a little bit on a tangent, but I don't know if you are familiar with the work of Daniel Frankel, who wrote a paper about the Doppler effect. And he said that if you treat the Doppler effect as a classical effect, the motion of the source with respect to the medium and the motion of the observer with respect to the medium, and then you use those two velocities to algebraically find the relative velocity, it reduces to the special relativity equation for the Doppler effect. The one caveat, though, is that when you're measuring velocities, you have to use the relativistic law of addition of velocities for those two to become algebraically identical. And the other thing I'll just mention in passing is he only did it for one dimension where all velocity was on like the x-axis. He didn't do that algebraic for three-dimensional motion. But I think it's an interesting paper to look at, and because you really see how two totally different physics models can be algebraically equivalent if you manipulate the math.
Okay, I don't think I'm familiar with that. I may have heard of it, but I'm not familiar with the paper, Nick, so it might be something to look at. And it does sound to me as if he's showing something similar to what I was expounding, that in tandem, you have the Einsteinian velocity composition rule with with the whatever equations they're using, the modified equations based on the Lorentz transformations, which actually modify, they simplify actually in a way the classical Doppler equations. So they go in tandem. And yes, you cannot have one without the other. They must go together. But they can be arrived at from different models. And I mean, I'd be interested in putting it back a bit to you, Nick, because you've done so much work on the Lorentzian ether theories that I'm just wondering, would Lorentz have exactly those same formulae for Doppler effect as Einstein, or would he be near to the classical?
Yeah, I have to defer on that because I focused entirely on kinematics and not electromagnetism. Okay. I'll just make one final little note here is so for listeners, you've shown that the velocity of the source doesn't affect velocity, but the velocity of the source does affect the frequency.
Yes,
as in the Doppler effect.
Yes, quite so.
Yeah.
Yes. Yeah.
That's it for me.
Well, thanks very much for that. That's all interesting. I mean, this actually did get me thinking. I've obviously been thinking about this for years and years, but when Denny suggested that I might give a little talk to indicate how the speed is variable, it just got me thinking, and I knew I had very little time, so I'm sorry if it was a bit rushed. I'm always more comfortable when I know I have plenty of time and I can bore the hell out of you. When I'm a bit short, I speak very quickly, and but it got me interested in many other things. I had already come upon the bit about the similar, the demonstration of the non-symmetry between observer and source, between all these experiments where people haven't seen it, like the Romer experiments and the Sagnac experiments and Michelson Gale and all that. But it got me thinking about that. And I did a little more research on the origin of the Sagnac, Sagnac, because we talk about the 1913 advent of Sagnac's work. And Sagnac actually had gone out to indicate that there was an ether, because he accepted that from the theoretical point of view, and he conceived that he'd disproven the earlier ideas of Einstein and Poincaré and so on. but there were earlier experiments done which are not usually put into the literature, like the one by Harris, Harres, in 1911, and the Pogany experiments in the 20s, and most particularly those experiments done in Paris during the German occupation, which seemed never to come out, not only during those first few years, but they never came out. I think Al Kelly actually got some of those papers in University College Dublin here, and he had to cut open the papers. They hadn't even been read by anybody.
What about Herbert Ives? You looked at any of his work?
Yeah, Herbert Ives. Herbert Ives' work. I thought you were going to say Herbert Dingle, but because you're talking about him the other day. No, Herbert Ives.
I think I got his first name right.
You did, yeah. I believe it's Herbert Ives, and he did a lot.
He's another one that had an ether theory that they kind of co-opted. They kind of stole the Ives Stilwell effect and claimed that it was proof of relativity, when that wasn't his intention at all. When he did the experiments, he thought it proved the existence of ether.
Yeah, that's right. He would have been contrary to the explanation of the special relativity theory totally. Yeah, and he did a lot of important work in early transmission of electromagnetic radiation for television and things like that. But it's actually paradoxical. I think we've discussed this recently as well. It's paradoxical how not only have they dismissed the work or dismissed the importance of the work, but they've actually turned it around to indicate in their words that not only did it disprove the usual conceptions of free space and indicate that there was an ether, but they've actually twisted around to say that it actually is one of the proofs of the special theory of relativity, which is given in the textbooks, which seems completely perverse to me.
I have a sort of issue with this Hertzian electrodynamics, but I got a question for you. You may not have an answer. Is the electric field and the magnetic field in phase, in your opinion, or not?
Okay. This is an interesting point, which
well, this gets to the problem of if you accept an ether and the ether is the medium, then a lot of people maintain that the electric field and the magnetic field have to be out of phase, because that's what, because the one represents an exchange of energy between the magnetic and the electric fields, and that's how the medium propagates the quote wave.
Yeah, it's the old chestnut, and it's quite interesting. I'll give you my view. I mean, I'm not afraid to give it, but obviously one could do a lot more work, and I've had a quick look at this. My own conception is to disagree with that. I put my cards on the table. I lay my cards on the table. I say they're in phase. I accept the conventional diagrams, which they produce from just some of the measurements. That you have this electric field and this magnetic field, and they're at right angles, and they're in phase. Now, I am familiar with some of the arguments that have been made that they're out of phase, and I did a little more research. I was in correspondence with a few people about this, a few in our group actually, and I came to the conclusion after doing a little work, maybe it's not the definitive conclusion, but I came to the conclusion that they are in phase, and that doesn't contradict in any way the existence of this ether.
But my question is, didn't Ed Dowdy deal with this in his extinction shift theory? Have you looked at that?
I-
Is there a similarity? That's why I mentioned Harvey, because Harvey seems to be more knowledgeable about what Ed Dowdy did.
Do you mean the gent who's joined our conference today, whom I haven't met before, Harvey Scribner? Yeah, is that who the Harvey you mean?
Yes.
Oh, okay. Well, he might in a minute come in.
Anyway, the
No,
point
Harvey.
is
Harvey.
that if
Yeah.
Dowdy, as I understand it, and I don't know if you ever, he was a longtime member of the NPA.
Yeah.
And I remember listening to several of his talks where he talks about this extinction shift, which looks to me to be sort of a Doppler shift theory. And so, to me, what's peculiar about the Lorentz transform is that if you look at the light clock, okay, they say, oh, well, this is the light clock. And where you have the light bouncing back and forth between a mirror, you get the same time dilation as you do from the Lorentz transform. So that tells me that maybe the Lorentz transform has some physical meaning, but because it's all kind of confused and everything that Einstein said and did, that we don't really understand what's going on.
Well, the original Lorentz transformation about traveling through the ether, the correction factor comes from the Pythagorean theorem, and that's where the square root of 1 minus v squared over c squared. So that's the physical model behind the original Lorentz transform, and Einstein just translated it into something that really doesn't have a physical model under it. It just really that each observer sees himself as the single observer in the preferred frame, which is, contradictory, inherently contradictory.
Well, listen, I'm kind of puzzled by, what Dowdy says, and that's why I brought it up.
Yeah. I'll just say a word about that. I'm just checking something here because I think the extinction theory of light dates back further. There are people like Ockert, maybe about 50, 60 years ago, who introduced it. It probably goes back further.
Yeah.
But my own experience, just briefly, is the following. When I talked first to sort of the group of people with whom many of you are associated, I think it was the old NPS actually, I think it was probably 2013, Ed Dowdy attended, and he had some very complimentary words to say at the end of the speech. He said something like, Ian, I think a lot of your ideas are similar to mine, and he went on, and he asked me one or two questions. Now, I've looked at some of his work in the meantime, and I think maybe you're right, I don't know, Nick or Harry, that there are some similarities, but I'm not actually convinced by the extinction system as a model. I don't know, it might be useful. I'm not sure how far it goes to one of his central theories, which is promulgated a lot, that the deflection of light about a star only occurs in its sort of coronal field, and whereas I don't think that's correct. I think a lot of people think it's correct in the distant circle. I think it's a gravitational effect. So I'm not sure about Ed Dowdy. I think a lot of his ideas are interesting, and there may be similarities. All right, there may be commonalities, but I certainly I'm not a follower of his per se.
He did say something, what you just mentioned about the coronal atmosphere. The way I understand it was, so there is the light doesn't go through the sun, it goes through that atmosphere, and he's saying the energy in the atmosphere, the coronal atmosphere, or whatever the plasma atmosphere, it has a certain density, so it refracts the light, and that density does have a gravitational component because it takes so much. It has a density, and it's actually held to the surface of the sun by its heat content, so kinematics or whatever, so that if the molecules, this is me talking out loud, and I may have some, I'm not a thermodynamics expert, but as long as none of the molecules don't have escape velocity, right? Energy. Then they will hug the surface of the sun. And so then it's refracted there. So the gravity formula is not the Einstein's theory of relativity formula. It's the gravity of the energy of the fluid, you might say, or the gas has the right density and held to the surface of the sun by gravity, the mass of the sun. Now, people are arguing the electric universe, like, what is gravity? Is it really an electric effect? But I'm not talking about that. I'm just saying, so then outside this surface, it gets really thin when you get really, right at that one point outside that atmosphere. When you get right above here, even spaceships, right? If they want to land in this Earth and they're in outer space, there's a certain cutoff point. And I'm not an astrophysicist on NASA, like NASA, but there's a certain point. If they don't have their heat shield just right, they'll hit that denser atmosphere and they'll deflect off and they're lost and they're dead. They're gone. So that's his relationship to gravity.
And I don't discount it. To me, those are secondary effects. I mean, what I actually take is the basic Newtonian deflection of light, which was calculated by Soldner in 1801, von Soldner, which is half the value of the Einsteinian value. And I take Dowdy's principles about the coronal, and you've explained it insofar as it might be allied to gravity. I take those as secondary effects. But anyway, I haven't studied in detail. To me, I've had a quick look at it to see whether any sort of commonalities with my own ideas or any contradictions, and that's so far as I've got.
Ian, Dowdy says that the NASA data shows that there is no bending of light beyond the corona.
Yeah.
Yeah.
Well, if that's true, and he worked for NASA, I believe, but
yes,
if that is true, that would point very much in the direction of his thesis. But I haven't seen that elsewhere. I've seen that any experiments, and I do think that the accuracy of the experiments is not such to distinguish between maybe the Newtonian and the Einsteinian value even today. But I'd like to see a lot more experiments, and I'd like to see other people say that as well. I've only heard that from Dowdy. Nick.
What he's saying is that here's the radius of the sun. Let's just say that's the radius of the sun. I'm not sure if it's 1/400th or whatever the atmosphere here. But if you go 2 times the radius right here, you should get 1/2 the bending, and you see 0 bending out there. If we saw bending out here that was 1/2 the angle, you could almost say that in all of space, there's stars behind stars, behind stars, behind stars, and the whole sky would be fuzzy because every star would be bent by the light of the other stars way behind it. Or, I mean, maybe I said that backwards, but that's the kind of general concept right there.
So the question is, does it bend off as 1/r, I think, or does it suddenly stop, effectively?
Yeah, it's 1 over, right. It's 1 over the angle. The angle should be 1/2. If you go double the distance, it would be 1/3 if you went triple the distance. And we don't see that. That's not observed. That's what he was saying. It drops off very quickly outside the atmosphere.
Well, NASA would probably not want to broadcast this because NASA is firmly in the camp of general relativity.
Right.
It's very different. Like the medium which is actually responsible for carrying the radiation, whatever about creating it, it is the system which actually transmits. It's exactly the same in water. If you have a source which is creating maybe water waves and it's moving within the water, well, the actual pressure waves are contained within the water. It doesn't matter how fast the unit which is actually creating it is going. It's not a sort of an additional velocity, a ballistic system where if you have a cannon which is actually moving along a rail and then emits a ball, well, you obviously have to add the velocities there, because it's a particle system. So I think actually, unfortunately, the particle, the photon system, you know, it has a lot of uses, but it's blinded us a lot to the essential wave nature of light. And if we kept that in mind, I think we'd never, you know, dismiss the idea that you know, it's really maybe in a medium, or even a quasi medium, if you want to use the term, which is carrying the wave at this speed, which is actually, you know, to boot, a function of the properties of that medium, you know, the electric and magnetic permeability and permittivity of the medium, which gives the speed.
Okay, so what I did was I also discovered this on my own, and I did this about 6 months ago or so. If you take a source, right, and okay, it's just a positive or negative charge, and so the standard modeling might say is the electric field is going out. If it's positive, the electric field is going in if it's negative. So you put another source, another test charge nearby. It'll either have a repulsion or an attractive force, right? And that force is called the, well, it's the electric field, QE, right? Force is equal to Q times the electric field intensity. Okay, so I looked at those equations, and the thing is if you, you can, if you do force equals Q1, Q2 over 4 pi epsilon naught, you get epsilon naught in the bottom half. And that's the permeativity of free space, correct? So now if you move that charge, and I put this in, if you move the charge, you'll get a magnetic field that will have a total field intensity right here. That's the Biot-Savart law, right? You'll have a magnetic field that's pointing this way or that way, depending on which way you're moving the charge and what, if it's a positive or negative charge. And you'll get mu naught. You'll get the permeability. Is that what it is? Yeah, the permeability.
Magnetic permeability. Yeah.
Yes. Okay. So here's the point and the aha moment. If you remove the source, well, first of all, they use those two permeativity and they put it in the wave equation that you showed, except for they don't add this V in there plus C. And then they say, oh, the partial derivative of space divided by the partial derivative of time equals, oh, squared equals C squared. So then you can say, oh, C equals 1 over the square root of epsilon naught mu naught. In the, and that's going, aha, everybody accepted Maxwell's equations from that point on. And it was proof of the theory of relativity. But if you remove the source in that has the electric field emanating from it, and it's not moving either because it doesn't exist, space itself has the epsilon naught and mu naught go to 0, or they would be 0. They don't exist because there's no charge present or no matter present. And so I'm not arguing that today there's fields everywhere and there's particles everywhere, so everything's present. There's, you know what I mean? I'm arguing that if we had this thought experiment where it was empty space, the velocity of light or of light propagation could be infinite because it would be a division by 0. That
it raises the very important philosophical point as to whether the ether, if you may use the term, has certain inherent properties independent of any apparatus that you put in to measure it. You see, you seem to have made that point, which I'm not so sure of. You know, I would maintain that the ether has inherent magnetic and electric properties that you just described a moment ago, and that's independent of whether you have particles there to measure it or not. In the same way that you would have that for maybe a resistive element, a piece of metal or something like that. It has an inherent conductivity or resistivity. The same thing with the ether. And I use, by the way, 3 parameters. I use the electric permittivity, the magnetic permeability, and the conductivity as well, which I take not to be 0. And that basically would be the the non-ideal case, just like the friction in the case of Newton's first law, which ultimately, it's very, very small, actually. It might be 10 to the minus 27 Siemens per meter or something, the conductivity, but it would lead to a diminution of energy, and therefore a redshift in any energy which is coming from very distant parts of the solar system to the observer. So I'd say.
Okay, well, I've got some comments. If you are interested in this, and may not. One of the things that the Lorentz transform seems to be controversial into how it's derived. And one of the issues is that he uses V plus and minus C. Okay, so he adds V plus C, and then he takes, he adds velocity V to the speed of light and subtracts it from the speed of light in his calculation. Do you recall this?
You said Lorentz. I mean, I certainly recall Einstein doing that, Harry.
That's what I'm talking about. I'm talking about the Lorentz transform that Einstein derived.
Yeah, I do remember that, of course.
Okay,
yeah.
so this raises the issue of, of what the heck's he doing if he's saying the speed of light is constant? Why is he adding and subtracting V?
That's the exact question that formulated itself in my mind some time ago. Yes.
Well, apparently what he's really talking about is the average velocity, the two-way light velocity, not the one-way light velocity, when he derives the Lorentz transform. And this apparently is a big point of confusion. So, you sort of are left wondering, what's he really doing? He's sort of saying the ether doesn't exist, or it does exist, but he's deriving the Lorentz transform based on an assumption that the velocity of the speed of light is different because it's C plus V, C minus V. What's he doing? Well, apparently he's talking about two different things. The velocity, he's talking about an average velocity of light is constant, not the one-way. Well, the two-way or the average velocity is constant, not the one-way velocity. And you think, oh yeah, now he's talking about something different. But then what he does is he substitutes the Lorentz transform into the one-way light equations when he does the light sphere. Okay, and so now it's the one-way velocity of light's constant, not the two-way velocity of light is constant. So it looks to me like that somewhere or another, the V plus and minus, C plus and minus V is in the Lorentz transform. That's what gives you the Pythagorean triangle thing. Okay.
Yeah.
That's somehow fundamental to everything that's going on in the physics. And so the question is, because Einstein seems to have confused people, like, whoops.
Are we going out?
We got Harvey's picture here. That's the triangle.
Yeah.
And that's basically the light clock thing.
Yeah.
Because you get the D when you calculate the time to go across the diagonal, that's equal to the time dilation. Okay. So if the light signal is going up and down with L, then, you say that's the rate of the rest clock. But when it's in motion, the rest clock is changed to this delta T prime thing. Okay, and that's time dilation according to the light clock, which doesn't really make any sense, because if you believe this, then the principle of relativity can't apply, because that can only be true if you have a rest frame that has a constant where the velocity is C and not anything corrupting it. There's no plus or minus V. But now when you're going in motion, you get this time dilation. So that goes to what I was saying before, which is the principle of relativity doesn't make any sense. this would be Lorentz's theory. Lorentz would say, if I'm traveling through the ether, I have a time dilation because of the traveling of light is longer over the hypotenuse. Okay. Do you follow what I'm saying?
Yeah, I do. And just two comments, maybe. I'm afraid we could have. One is that, yes, for this light clock type construction, in 1881, when Michelson performed his first experiment, he didn't have this dilation in. He actually said the orthogonal ray, the one at right angles to the direction, it did not have an effect. It was just 2L over C. And Lorentz came in and he said, no, you must put that in. The second point I would mention to substantiate what you're saying, Harry, is that you remember in my formulae, the classical formula for the Doppler effect has V plus or minus C, S or O. But so does the relativistic one. It has V plus C and V minus C. And actually in the textbooks, that's usually disguised. They usually take the factor out, say of C, and they have C into 1 plus V over C. So it looks as if it's innocuous, but actually even the relativistic formula for Doppler has V plus or minus C in it. So it is a contradiction, yes.
Well, my feeling about it is, if you recall my little presentation where I said, I don't think that the principle of relativity is true. And you can look at it at different ways. You can say, I don't believe in the C is constant. You can, you could say one of the two postulates is false, or you can say both are false. I don't know. It's just too confusing. But it looks to me like that an essential feature of the Lorentz transform is that the velocity of light in the two different directions can't be the same. So in other words, the velocity of light going in one direction can't be the same as the velocity of light going in the reverse direction. And so it's just confusing mess in my mind. I'm not really sure why people think that he's saying the one-way velocity of light is constant. That doesn't appear to be, it's confusing.
Yeah,
Sorry.
well, but Harry, in the Einsteinian synchronization of clocks, he tacitly assumes that it's the one-way speed of light is C.
Yeah, this is where you're kind of like going around in a circle. If you adopt the Einstein synchronization, which it kind of assumes that, so you're not really sure what he's talking about. He doesn't really, what time isn't really nailed down in his theory. It's just becomes whatever, it seems he's talking about at the moment. Is he talking about that? My personal opinion is that there's this confusion about time. He never really defines what time is. Is time an interval, or is time like a date? And by talking about synchronization in the beginning, he implies that time is a date. You know what I mean by date? It's like what the clock indicates at a particular moment in time. Okay, but then when you do the equations, you do the equations for the light sphere, the time is an interval of time. Okay, it's time from 0 to some t time. And then the light sphere at some t time is at a certain position. So time is not the same thing as time as a date when so you're confused about what he's talking about, to the point where you don't understand it. I don't really understand what he's saying, frankly.
But it does appear that the composition of speeds formula does come out of the Lorentz transform. So I don't know if he's addressed that specifically. I mean, Einstein did, but if you just work out the difference in time and difference in distance from the Lorentz transform and just work out the velocity from it, you will get this non-simple expression v1 plus v2 over 1 plus v1 v2 over c squared, which I
think that the Lorentz transform is basically telling us something about this Pythagorean theorem triangle, and I think it's telling us that motion is absolute relative to the rest frame. Okay. And I think that's what the Lorentz transform tells us. I think Lorentz was right in the beginning. And then Einstein sort of messed things up by saying, well, I'm going to invoke the principle of relativity. And then things got real messed up after that, because he tried to take Lorentz's theory for motion through an ether and then turned it into a motion through space that didn't have an ether. And
that's all very well, but you must remember, coming back to my thesis, that Lorentz and others like Lormer first derived this as an expression which would permit invariance in moving from one frame to another in electrodynamics. They found that this was the transformation which would do that. Now, I say that is osios, to use my word. It's unnecessary, because if you had started from the correct equations of fluid dynamics, all you would find is the Galilean transformation.
Well, yeah, but somehow you got to get this Lorentz transform in there. I mean, it's got to come from someplace. I mean,
so which place did it come from first? Like, I might maintain that he started with the electrodynamic derivation of it, and then he used all this type of physics and light clock systems to justify what he'd already defined. It's a bit of chicken and egg situation, Harry, I suppose.
Well, Ian,
yeah,
Lorentz's Lorentz transformations were built on clock retardation, and GPS says that's physical reality, and that physical reality is not built into Galilean transformations.
Yeah, that's a good point, Nick. I suppose I would probably answer that by saying that it's somewhat of a coincidence, one might say, but the fact that atomic clocks are retarded via velocity effects and gravitational effects, admittedly relative to a preferred frame, an ether frame, if you like. To me, that's another matter altogether. It's to do with the vibration of atomic clocks. It's not something inherent in time at all. And I think maybe it's not surprising. I mean, if you have V plus C and V minus C, the things we're multiplying about, and you just multiply them together, you get V squared minus C squared. And just divide that by C squared, you get 1 minus V squared over C squared. So maybe it's not surprising that this Lorentz factor comes in to all different types of disparate, endeavors. Yeah. That would be the provisional explanation I would give for it. It's a good point, Nick. But I wouldn't throw out the Galilean transformations, because it doesn't in itself.
Well, yeah, and I'm not really sure that we're talking about the same thing. I think this business about the Lorentz transformation reduces to a Galilean transformation. I'm sorry, I don't. To me, the Lorentz transformation is talking about light spheres, the velocity of light. How does that have anything to do with the Galilean transformation? The Galilean transformation talks about how objects move in space, a particle, not necessarily a light wave.
Okay, here's my key point again. We have to specify which version of the Lorentz transformations we're talking about. You're talking about the special relativistic one, whereas Lorentz's original transformation didn't have that problem.
Well, supposedly the Lorentz transformation is supposed to tell you that the light sphere in the rest frame and the light sphere in the moving frame are equivalent. Okay. And
well, I think you're talking special relativity there.
No, that's how the Lorentz transformation is derived.
Okay.
Okay. Now the question then comes to, special relativity says that you can, because of the relativity principle, you can reverse the frames. That's where the problem arises. If you're only talking about a transformation from the absolute frame to the moving frame, okay, then the Lorentz transformation seems to work under with restrictions. It doesn't work in the negative direction. It works in the positive direction. That's kind of a problem. But it seems to work there. So, you know, and since they only do experiments from the rest frame to the moving frame, and they don't actually reverse the frames, they say, oh, this proves special relativity. But I see they've only proved Lorentz relativity.
Yes.
So it's, my question to Ian is this. Could you derive the Lorentz transformation from the full derivative equation, the Hertzian equation? Does Hertz derive the Lorentz transformation? Can you get it out of the Hertz system of equations?
Yeah, this is the central. Are you still there?
Yes.
Oh yeah, sorry, I thought we were cut off from that.
No, I just
think I don't know how much. Yeah, it's just the Harvey slides. I don't know how long we have, but basically this is the nub, Harry. Do you see? You can't really, because Lorentz transformations are one way of establishing invariance, or one type of transformation, one type of group, if you like, which will permit you to transform from one to another in an invariant way. Now, if you use Hertzian dynamics, you get equivalent. There was a cross term there that I said it came into the Hertz term, which didn't come into the Lorentz term. But basically, you get an equivalent system. But you don't get the Lorentz transformations. If you said, I don't know what transformations to use, but I know that Hertzian electrodynamics is correct, and you worked out the equations, at the end of the day, you'd get the Galilean transformations. You wouldn't get the Lorentz transformations. You'd get X equals X.
That's why you're saying it's irksome or
Otiose. Yeah.
Otiose, or
Yeah.
whatever, how you pronounce it.
That's right.
But you sort of have to still take into account clock retardation as a function of absolute velocity.
I take it into account as a function of absolute velocity, or as I'd express it, velocity relative to the ether. However, I'm not even sure if retardation, I'm not going to argue with you about the term. I'm just worried that the same term is used for Lorentzian dilation, and it's quite a different phenomenon. It's not related to it. It's another matter altogether. It's a physical phenomenon to do with atomic clocks. If you had another means of measuring time, I maintain you wouldn't get it. It's not a time function.
All right, but I'm saying that you have to do away with time. Time is a red herring. All we have are processes, and what drives all clocks, including atomic clocks, are processes.
That's true, but what about the fact that you can synchronize clocks around the nearest planets of the solar system? That tends to argue that there is such a thing as time, and it's real.
No, what you have are the fundamental physics is processes. But all processes can be related one to another. It's just easier for humans to think in terms of minutes, seconds, hours, which their derivation was always some physical process. You have never measured time. All you have ever measured is a process.
Yeah, that's the way it originates, but I don't dismiss it altogether. It's a geometrical idealization, just as our spatial coordinates actually are a generalization of geometry. Is just measuring the Earth. We put rods down and we measure things and we try to construct things, and then we talk about an ideal X, Y, and Z direction. Do they exist? Well, I don't deny that they exist, but they're idealizations. The same with time. I believe that there are time differences in processes. You have one process there, and later on you have it in a different state, and the difference would indicate the time in which it occurred. But time itself, I don't say it doesn't exist. I say it's an idealization of the process.
Yeah, and I say quite differently, that it's a generalization of processes.
So
There
now
is
we're
no
back to-
physical counterpart to time.
So now we're back to the whole issue revolves around what's the definition of time that you're using in your theory.
Yeah, so Lorentz, it was an improvement in only talking about clock retardation and not about time itself.
Ian, is something on the lines of that the atomic clock, the retardation of the atomic clock is not really, although it might indicate that the Lorentz transformation time dilation effect is correct, that you would say that that's really an effect of the physical mechanism of the atomic clock operation. Does that summarize what you're saying?
That certainly is my position. Yes.
Yeah. And I would agree with that.
Oh, you agree with it, Nick? Okay. So then, Nick, do you think that for ordinary mechanical processes, the Lorentz transformation does not apply, but the Galilean does, or do you disagree with that?
If you're going to get a transformation, you have to factor in the fact that clocks, which are part of doing key measurements in physics, are altered by absolute velocity. Atomic clocks.
Atomic clocks, yeah.
Atomic clocks. Other clocks are affected differently. So it's pretty easy, I think, to show that time does not exist because, you know.
Well, you said a moment ago it's a generalization, so maybe it's a question of terminology and philosophy.
No, it's generalization says that happens in our minds. And we pick certain processes to be the standard processes so that we can talk about it, rather than talking about the rate of every single different process and how hot what the temperature is and the pressure and the velocity and the thickness of the air. We're real world things. So it's just a simplification of process rates, process length.
Well, if everything were static in the universe for all time, I use time, but if nothing changed, I suppose we could dispense with time, but that's not the case. There are processes.
But let me add one thing there. If you add energy to that static universe, then you start having motion and change, and the perception of time comes in, but you haven't added time. What you've added is energy. It's very hard. Ever since you could understand words, your mind has been using the concept, the generalization of time. And for a young child, trying to make sense of the universe and all these different things happening is a great simplification. And they learn, okay, a second is about this much duration, and an hour is this much, and a day is this much. So it gets embedded in your mind since you're about 1 or 2 years old.
So
but there is an analogy, you know. I mean, in mathematics, we do. I'm not going to start talking about dimensions, but we do, you know, express the variable u in my equation there in terms of x, y, z, and t, and the x, y, z coordinates are generalizations of, you know, when we were little babies crawling on the ground, we could move in 3 directions or 2 directions. And they're generalizations of those, and they're put in the mathematical form. And maybe time is a similar thing.
Well, there's a qualitative difference there, because measuring space intervals have always been done in terms of space intervals. But measurement of time has never been in terms of time. It's always been in terms of process length. So there's a qualitative difference there.
Well, now we're back to the problem of you have to really nail down what you mean by time. And I think Einstein confused that by talking about simultaneity. And that's not really the same thing as time, in my opinion.
And he really confused it by saying time has its own dimension. Once you get used to the idea, you talk about all processes unfold within three-dimensional space. A fourth dimension is superfluous or odious.
Yes.
Well, to solve the mathematical equations, you do have to have the four equations in, the four
parameters, right?
Parameters.
And one is process rate. It's not.
Yeah, well, you could call it what you like. I mean, it's an idealization. All processes are pretty inexact. I mean, and they change and they have various, disturbances. So we idealize this.
I like the concept.
Margaret Walton, I'm sorry, go ahead.
I like the concept that the stuff that exists in X, Y, and Z dimensions of space is like the data. And the time is an application of certain time development laws to that data, like the clock of a computer may modify the data in RAM memory. So I see the time as it's confusing to mix that up by multiplying it times C and to get a meter's value as confusing.
Well, yeah. Margaret Walton, I tried to convince her to give us a talk. Dennis, I may recall that. She says that the issue has to do with confusing time, which is a parameter of an evolutionary process. So in other words, time is a process parameter, as Nick says. It's a measure of the process, okay? And therefore, since it's a process parameter, it can't be a dimension. And you can't...
Exactly.
And
You're talking about Gertrude Walton?
Yes, did I say her name wrong?
Yeah, I forget what first name you used. Oh.
You said Margaret. I hadn't heard of it.
Oh, Gertrude Walton, is that her name? I get confused with names. Okay, but anyway, that's the point. The point is that time is a parameter of the evolutionary process. Okay, it's a parameter. It's not a dimension. It has to do with the description of the process. Okay, and so since it's not and what relativity does is it treats it as a dimension of space and time. And that can't be correct because that's not what time is. Time's not a dimension.
Right.
That seems to be the essence of her argument. So that leads you to, so she rejects relativity on that basis pretty much alone. That's it. That's all there. Relativity is not worth talking about anymore because its concept of time is completely wrong.
And even worse, it combines it with space and has space-time where time can morph into space and vice versa. Thanks.